Hey, welcome everybody to your first APChem vodcast on Chapter 4, Aqueous Reactions and Solution Stoichiometry. Please make sure you have your packet out for your notes outline. If you don't happen to have that, it is linked onto the homework page. All right, here we go. Beaker's got some vocabulary words for you need to know. So let's talk through them briefly. Solution is a homogeneous mixture of a solute and a solvent. We typically make them in volumetric flasks so that they are very precisely measured. Solute and solvent are really important, and it's important to be able to tell which one is which. Now, usually it's a solid dissolved in a solid solute dissolved in a liquid solvent, but not always. Let's say air, for instance, two gases. How do you tell which gas is the solvent and which ones are the solute? Well, if you notice, the solvent has far many more molecules than the solute. So nitrogen in air would be the solvent. Oxygen, argon, carbon dioxide, water vapor, those would all be solutes. When you mix a solute and a solvent, if the solute is ionic, you're going to have dissociation going on. That's just what's happening here with the ions being surrounded by water molecules and separating from the other crystalline ions. Because those ions are now dissociated in water, they can make an electrolyte, like Gatorade. An electrolyte is something that will conduct electricity, helps your muscles, send signals to through your nervous system, and it's important to have enough electrolytes. If you are drinking just sugar water, not an electrolyte, not going to conduct electricity because sugar is molecular and is not going to form ions or charged particles in the solution. All right, so as Beaker and Bunsen are showing you here, if you have the soluble salts in your solutions in your body, you're going to conduct electricity, which can be a good thing. Not necessarily the way these two are doing it, but if you have an ionic compound, they are all strong electrolytes if they dissolve, and some molecular compounds are strong electrolytes as well, such as strong acids. Talk about those more in a second. Okay, molecular compounds, such as the ones depicted here, are non-electrolytes. Anybody remember what this is? CH3OH, methanol. Of course, this is our friend H2O. Neither of these are electrolytes by themselves because they don't form ions. There are some exceptions to this rule. Yep. Acids and bases. So let's talk about those. A strong electrolyte, such as the ionic compounds or acids and bases, will form many, many ions in solution and thus conduct electricity, lighting the light bulb. Weak electrolytes just form a few ions. Some things stay as molecules and some separate as ions. So that will conduct, but not nearly as well. If you want a strong electrolyte, you're going to have to use a strong acid or a strong base or the ionic compounds. So let's focus on what are the strong acids and strong bases. There are 7 known strong acids and strong bases. You will be required to know these because you need to know in a reaction whether they're forming ions or not. One hint here is none of these are organic, non-carbon containing. They're all the mineral acids. And then the strong bases are all hydroxides, and they belong to group 1 and group 2 parts of the periodic table. If you look on the periodic table, you've got the group 1 metals, and then calcium, strontium, and barium in group 2. Notice that forms a B for base. Okay, also making strong electrolytes are these soluble ionic salts. Sorry about that. A few of these rules that I'll point out right now are that nitrates in a salt always, always, always are soluble and always are strong electrolytes. Acetates, always soluble, always strong electrolytes. And then some things that can make other things soluble, like hydroxides, are typically not soluble, or phosphates or carbonates or sulfides. But if you mix them with alkali metal cations, the first group, or ammonium, those are always soluble also. Ammonium compounds, alkali metal compounds, nitrate compounds, and acetates. One little help to the solubility rules. All right, today we're going to talk about one reaction type, metathesis, which in Greek means to transpose. In a metathesis reaction, double replacement, the cations and the anions trade partners. Silver will now be allowed to bump into chloride, and potassium will bump into nitrates, and sometimes they stick. Good question, Janice. Why wouldn't they keep just bouncing around? Why do they stick together? Well, Janice, you see some ions come together in a permanent way, solid, a liquid, or a gas. That's because the water that would dissociate them doesn't have a strong enough bond to tear those things apart. So it's all about relative bond strength. All right, first subtype is the one that we are pretty familiar with, is a precipitation reaction. If you form a solid, something that does not dissolve in water, such as lead iodide, this pretty yellow stuff, then you've got a double displacement and you will cause this reaction to happen. When you write these as a molecular equation, which we have all done many times, you've got usually two aqueous compounds forming a solid and another aqueous compound. That's useful, but that's not really showing us exactly what's going on in the reaction. So we also need to remember how to write ionic equations. In an ionic equation, anything that's a strong electrolyte, soluble ionic compounds, strong acids, strong bases, are dissociated. So you see them separated here as ions. So you got silver, nitrate, potassium, chloride, all as ions. The only thing that is not an ion is this silver chloride, which stays together because water can't dissolve it. Okay, that more accurately describes what's actually going on. Okay, so we want to be able to write the net ionic equation of what's really going on so we can take out the spectators. If you remember, spectators are anything that is in ion form on both sides of the reaction. Potassium ions in this case, see, they're both ions in the reactants and in the products. And then also the nitrates. Even though we can see silver and chlorine on both sides, they're not in the same state. The silver ions and the chloride ions are aqueous, and the silver chloride is a compound, no free-forming ions, free-flowing ions. So when you leave out the spectators, just cross them out, that leaves you with silver ions plus chloride ions making silver chloride. That's really what's going on, so that's what we care about. So we're going to practice writing a lot of net ionic equations. Okay, another subtype are acids reacting. So let's go through quickly what an acid is by definition. Two two main definitions, one by Arrhenius, the simple one that defines acid as anything with a hydrogen ion being donated to the solution. This works almost all the time for our acids. Bronsted and Lowry broadened this definition a little bit to include proton donors. So it might not be a hydrogen donating the proton, it might be some other element. Okay, a base has Arrhenius and Bronsted-Lowry also. Arrhenius defined a base as something that donated hydroxides to the solution, whereas Bronsted-Lowry defined them as proton acceptors. I'll give you a quick example of that. One base that is not a hydroxide is ammonia gas. So ammonia, if it does get added to water or something that could donate a proton, will form ammonium ion. So it accepted the proton from the water to make a base. Now it turns out in this case, water leaves behind hydroxide, so it looks a lot like Arrhenius base too. But the ammonia itself is called a Bronsted-Lowry base. Okay, so the metathesis reaction that uses acids and bases is called neutralization. So as I just showed you in that reaction, you've got a proton donor in the water and an acceptor in the ammonia. And that leaves behind ammonium ion and hydroxide ion. So generally when you have an acid and a base, you form water from the hydrogen and hydroxide getting together, or the proton and the proton acceptor. And you've got a leftover salt, a leftover cation from the base and an anion from the acid. And the water is what causes this reaction to happen, the formation of a liquid that doesn't ionize. Okay, when a strong acid and a strong base react, you always get salt plus water, and the net ionic equation is going to be hydrogen plus hydroxide makes water. Simple stuff. Okay, finally, complication that comes up quite often is that some products of metathesis reactions aren't very stable and they decompose, often into a gas. Okay, for instance, if we have a limestone statue and there happens to be acid rain in the area, your limestone would go through a metathesis reaction to form calcium chloride, that's salt, and it would form, you would expect it to form H2CO3, but that's not all that stable, and so you'd get carbon dioxide and water. That's one that you should be familiar with because it'll come up quite often. Some other examples are baking soda. Put in a lot of baked goods because when it reacts with an acid or it's heated, it forms carbon dioxide and water as well. Sulfites often do the same thing. Sulfites will form sulfur dioxide and water. And the really fun one is when you have a sulfide and you form hydrogen sulfide. I think you'll remember what that's like when you get to make this in lab next week. All right, that is it for today's installment of AP Chem Notes on Chapter 4 Vodcast. So please finish filling out your notes outline if you need to, up to this point, and then fill out the summary online and submit to me, and that will give you credit for doing these notes. I'll see you in class on Monday. Have a great weekend. Bye.